He got the Nobel Prize for the discovery, well, almost 40 years ago, of superfluidity in helium-3, which has been very elusive for some years, and he will tell us the whole story, which is fascinating, about how the theoretical estimates went down all the time. Each time it wasn't found where they predicted, they lowered the prediction until finally they caught up with the facts. It's really a fascinating story. And I think the thing which is really very educational is for the younger people here, which are quite a few, that, you know, if you have the right equipment and if you are astute enough to understand that you observe something interesting and intelligent, and if you work very hard, and I think you will tell us about the night walk in the basement of Clark Hall, then you have a chance. With that, I'll give the mic to Douglas.
Is this one working? I get two microphones. I can speak twice as fast. This one or this one? This one. Okay, so I'll just leave it. Okay, I've turned it off temporarily. I don't know what to say. If this were one of the ordinary talks I give to audiences all over the world, I suppose I would say, Jin Tian Tian Xi Hao Ji Le, which means in Chinese, it's wonderful weather, and it is, unless you're up north. But we won't talk about that. Anyway, it's my pleasure being here. This is actually only my second trip to Israel, and I'm sure looking forward to it, the rest of it. I apologize for this. I couldn't find any of my pictures which were vertical, except for this one. That's Heidelberg Castle. Has absolutely nothing to do with this meeting, I suppose. Anyway, so this is, once I've given the talk about the discovery of superfluid helium-3, maybe the 100th time or 200th time, I decided that I would change it to the story behind the discovery. And so that's what you're hearing. And I hope particularly it has messages which will resonate with young people in the audience. So let's see what happens. Okay, so let me first start by talking about the early history of helium physics in general, I suppose, and that really has to start back in 1908 when Dewar and Camerlionis were in this competition to see who could first liquefy the lightest and most inert of the atmospheric gases, and it looked like Dewar had won when he liquefied hydrogen, but then already, I should say, people had obtained evidence for the existence of helium, which had really not been found yet on Earth. And within, I think, something like 10 years, Camerlionis was able to get enough helium-4 gas that he could attempt to liquefy it, and he succeeded in 1908. And then he did with the liquid helium exactly what Dewar had done with hydrogen. He pumped on the vapor above the liquid. Of course, that caused the liquid to cool, and ultimately he was able to cool liquid helium down to 1.04 Kelvin, and much to his consternation, it never solidified. Now, he actually spent 2 years on that, and eventually gave up and looked around for some other question of the day that he could answer with this rather unique refrigeration device he had. And so people were speculating as to what would happen to the conductivity of metals if they could be cooled to absolute zero. And one argument was that as you cooled them down, if it was a very pure metal, you would eliminate the vibrations of the lattice that scatter the electrons, so the electrical resistance would slowly drop to zero. The other argument was that at some temperature, the conduction electrons, which were, of course, free to roam around the interior of the metal, would recondense on the ions from which they had come, and all electrical conductivity would cease. And so he got a very pure sample of mercury and gave it to Gilles Holst, who I always think is his graduate student, but I'm not quite sure that that was their relationship. And Gilles Holst cooled it down and was measuring the resistance, and all of a sudden at a temperature, and in fact the resistance was slowly dropping, and then all of a sudden at about 4.2 Kelvin, the resistance dropped discontinuously to a value of less than 10 to the minus 5 ohms, which is the resolution of their instrument. And of course, that was the first observation of superconductivity. So I give a talk on, which basically talks about strategies for making discoveries, and one of them is if things are going badly, nature may be trying to tell you something and do something different, and you'll see that I did that as well. Anyway, then, of course, throughout the 1930s, I would say people started realizing the remarkable properties of this liquid helium at low temperatures. And in fact, Camerlone has actually written in his lab book that it appeared that the liquid helium stopped boiling at 2 Kelvin, but he never actually went to investigate what was happening with it. Of course, that was a number of people, Kapitsa, Allen, Meissner. However, only Kapitsa was awarded or shared the Nobel Prize for his measurement of the viscosity of helium in the bleak winter of 1937 in Moscow. He showed that the viscosity of liquid helium at suitably low temperatures was less than a billionth of a poise. Anyway, so over the decades, people began to think about, they knew, of course, that helium-4 atoms were Bose particles, and so it was easy to think about this as some consequence of Bose-Einstein condensation. However, if this is the thermal de Broglie wavelength, presumably Bose-Einstein condensation should occur when that became comparable to the interparticle spacing. However, what people knew was that if you compressed liquid helium, then you would expect that this term has to go down, and for that to happen, the temperature should rise. But that's the transition temperature. In actual fact, the transition temperature goes the other direction. So people still like to associate this, and in fact, when I was a first-year graduate student, I always thought of superfluid helium as being a Bose-Einstein condensate. That's not quite correct. So in 1957, on the other side of the aisle, that is the fermionic helium, well, this had nothing to do with helium to begin with, and that was the BCS theory finally explained the origins of superconductivity, which Gilles Holst had found in Camerleonis' laboratory. And, of course, it depends on the formation of correlated pairs of atoms, which we call, or electrons called Cooper pairs. And in that, of course, the correlation resulted from an attractive interaction mediated through the lattice, but I think pretty quickly people realized that in principle the lattice wasn't necessary. So, and now going on to helium-3, specifically, it was in 1948 that Ed Hamel, who was an employee at Los Alamos National Laboratory and was responsible for keeping the tritium clean as the U.S. Was in competition with the Soviet Union to make the first hydrogen bomb. So he would periodically sweep out the helium-3, and then rather than throwing it away, he saved it, and ultimately in 1948 he decided to liquefy helium-3 and measure its vapor pressure as a function of temperature. And he actually published these results, I think in Physical Review Letters, or whatever that was called at that time. And very quickly, the Russians started doing the same sort of experiments. Now Ed Hamel had actually said how large his helium-3 sample was, but the Russians never said how large their samples were. And Hamill figured that was actually the first serious security leak at Los Alamos National Laboratory, because by saying how much helium-3 he had, he was saying both something about how much tritium Los Alamos had and how long they'd had it, because of course the decay lifetime for tritium is 12.3 years. So people started looking at this liquid helium-3 and found that it did nothing particularly stupendous near the Fermi temperature, but a factor of 10 below the Fermi temperature, one started seeing evidence for Fermi degeneracy, specifically a heat capacity that was linear in the temperature. After that and the BCS theory, a worldwide search was on. There were specifically people, Phil Anderson, my dear friend, I think, claims that he was embarrassed that he had his name on a paper that suggested a transition temperature of 80 millidegrees. However, that was certainly unrealistic, but it got people looking, and in particular, not just looking for superfluidity helium-3, but developing new refrigeration technologies, which then would allow us to look at nature literally in a new and different realm. And I became a graduate student at Cornell in 1967, and by that time, John Wheatley's group, we were competing directly, I think, with Wheatley, had cooled helium-3 under its own vapor pressure down to 0.002 of a degree without seeing any evidence of superfluidity. So the common wisdom amongst the graduate students was that superfluidity in helium-3 was a pipe dream by the theorists. And of course, pipe dream, we're talking about something hallucinogenic or worse. Anyway, so here's the history, and we've gotten down to this point here, and this is about where I became a graduate student. But there were two things that were done just before I became a graduate student that really changed low-temperature physics. One was that David Edwards at Ohio State University found that helium-3 was soluble up to about 6% in superfluid helium-4 at low temperatures. And it took just about 1 year, less than a year, for Henry Hall in England to realize that you could use that to make a refrigerator that resulted, that depended upon the dilution of helium-3 into superfluid helium-4. Okay, now I'm going to talk a little bit about myself. I'm going back in time now. I think this is Christmas. Got to put my glasses on. 1953, yes. So my father was a medical doctor. I should say more than that. He was, I would say, a studier of all religions and a believer in none of them. He was of Russian Jewish heritage. He married my mother, who, well, wasn't my mother yet, of course, but who was the daughter of a Lutheran minister. Quite an interesting marriage, and had 5 children. I'm son number 2 here. My older brother went into medicine. My sister became a nurse. Anyway, so that's where I'm coming from, I suppose. And I grew up in a small logging town in the west coast of Washington State. I would say that the one teacher in my first 12 years of schooling that influenced, and I would say profoundly influenced the way I think about science was not my physics teacher, but my chemistry teacher, William Hawk, shown here. This strange-looking little character, that's me. And one day, William Hawk came into class, and he had a milk carton and something inside it, and he shook it and said, research is like trying to find out what's inside the milk carton. You can do an experiment, and every time you do an experiment, you're asking a question of nature. Nature has to answer your question, but nature's answers, nature being a woman, of course, are rather obscure. Pardon me for I beg my pardon of the women that are in the audience, but it makes for a nice story. Anyway, anyway, And then you have to do more experiments to constrain your interpretation of her previous answers. And that, to this day, is the way I think about doing research. What you're doing is you're asking nature questions to try to trick her into giving up one of her deep secrets. And to this day, that's the way I think about it. I went to Caltech for undergraduate school, and Richard Feynman was still teaching this marvelous 2-year sequence. My freshman class was 192, but only 120 returned for their sophomore year. I think Feynman's class was a brilliant filter to get rid of students that weren't really interested in going into physics. That fall of the sophomore year, you had to declare a major, and I think of the 120 that remained, fully 2/3 of those people wanted to be physics majors, and well, I was one of them. But I won't tell you the rest of that. Okay, after Caltech, I went on to graduate study, and after 4 years at Caltech with the terrible smog that they had in the Los Angeles basin, I decided to go as far as I could get from Caltech, which was Cornell University. So this is Cornell in the fall. I got this off the web. This is not one of my photographs. And so the first semester, there were 2 talks given. One was a solid-state seminar on the Helium-3, Helium-4 dilution refrigerator, and the other was a talk by Bob Richardson, colloquium on Pomeranchuk's refrigerator. And both of these seem to give promise of allowing whoever developed these technologies the possibility of looking at nature in a new and different realm. And so that's really why I went into low-temperature physics, because I really felt that this was going to be some excitement, and I'd always wanted to be an explorer. And, I mean, when I was a kid, we would walk along long, deserted logging roads that wound their way through the hemlock and fir forests surrounding Aberdeen, and we thought of ourselves as being the first people that had ever walked on these roads. Well, it didn't make any sense, of course, but anyway, so this is a Helium-3, Helium-4 dilution refrigerator. I guess the people that know about this technology don't need to be reminded of it, and the people that don't use this technology don't care about it. But the dilution occurs here in something called a mixing chamber, and I actually built a Helium-3, Helium-4 dilution refrigerator my first year of graduate study, which is shown here. So this is the mixing chamber. And up here, there's something called the still, and you pump on the still. It's a mixture of liquid helium-3 and helium-4, but the helium-3 has a higher vapor pressure, so you mainly are pumping out helium-3. Then helium-3 diffuses across the phase boundary between liquid helium-3 and helium. I'm sorry. I know I promised you I wouldn't tell you all this stuff. But anyway, this one got down to the base temperature was about 15 thousandths of a degree, which back in those days was pretty remarkable, continuous cooling to that temperature. But the other talk was based on a conjecture that had been made in 1950 by Isaac Pomeranchuk, who, of course, was a member of the Landau School. So Pomeranchuk was mainly interested in high-temperature plasmas, but when Ed Hamel published his results, Pomeranchuk started thinking about the properties of liquid and solid helium-3, and he realized that in the solid, the entropy would basically be that of a spin 1/2 system, R log 2 per mole, but in the liquid, he expected the entropy to drop rather quickly, and at low temperatures, if it exhibited Farabi degeneracy, it would drop linearly with temperature. And so you end up with a very unusual situation below the crossing point where the liquid is more highly ordered than the solid, which is kind of unusual. That means that the latent heat of solidification is negative. And what that means is if you compress and solidify helium-3 adiabatically and reversibly, that's, of course, the key, then, in fact, the solid that is formed will rob entropy from the liquid, and the liquid will cool rather rapidly. For every percent of the liquid that you convert to solid, the system would cool by 1,000th of a degree. You can decide whether that's rapidly or not. But the point is that with a dilution refrigerator starting at 15 milledegrees, if you solidified 15% of your sample, you'd be very close to absolute zero. So this is the helium-3 melting curve, and it below the point where these two cross, according to Clausius-Clapeyron equation, it has to have a negative slope. No one thought that this would work, and in fact, no one tried this until one of Peter Kapitz's students in Moscow tried this, a fellow named Onufriev, in 1965. So he started with liquid at about 100 milledegrees, compressed it up to the melting curve, and then followed the melting curve down, finally came off the melting curve at about 20 milledegrees. That was not actually as cold as my dilution refrigerator would get, but Dave Lee, my thesis advisor, didn't like to think about it that way. He said, if we can really do this adiabatically and reversibly, we start with liquid here, we form solid over here, where in fact the entropy of the solid has dropped because it has undergone nuclear spin ordering. So by the time I was a graduate student, the common wisdom was that helium-3 would never be a superfluid, but that in fact a nuclear spin ordering in solid helium was expected to occur at a temperature of about 0.02 of a degree above absolute zero. So that would limit the degree that cooling you could get with this technique, but that looked pretty impressive. So I was not the first one at Cornell to build a Pomeranchuk cell, as they're called. This was actually the design that Onufriev had. The idea is you have superfluid helium-3, liquid helium-3 in this yellow space. I always make it gold because helium-3 is such an expensive gas. And then you have a thin-walled container which you then fill with helium-4, and that expands it outward, decreasing the volume for the helium-3, and that causes the solidification. This is one that was, I don't think this one actually worked very well. This is one that was used by Jim Seitz, who was the graduate student at Cornell that I mentored under. And I dare say I think that Jim Seitz should have made the discovery that I made, and I'll explain why he didn't, and he agrees with that. This is my Pomeranchuk cell, and I like to think it's the best one ever. After all, it did the most work. So this is a helium-4 in here, and this is a helium-3 now in gold, and you decrease this volume by pushing a metal bellows in here with using a larger bellows to provide the force, and this was then connected to a capillary tube at room temperature, and then you just fill this with superfluid helium-4, which solidifies at 25 bars. The helium-3 solidifies at 34 bars. So you need to have this multiplicative factor, the ratio of these areas. And then to measure temperature, we would do NMR, look at the Boltzmann distribution, if you would, of platinum-195 nuclei. The T1 is very short in platinum, so it's a good thermometer. Platinum wires here, and then we measure the melting pressure with a capacitive pressure transducer that was actually developed at the University of Florida by Dwight Adams' group. These are some of the parts. As a graduate student, I'm sure most of you may, if you've ever done any building, will know the parts come out and they're shiny and they're beautiful, and there's nothing nicer than fondling is probably not the right term, but it's so nice, those parts. Anyway, yes. So as you can tell, I was a photographer long ago. So in the summer of 1970, I won't tell you the story of my meeting this little Chinese girl from Taiwan, and no, I won't do that. We will never have enough time, but we got married. She got her PhD actually 2 years before I got mine. She'd come to Cornell with a master's degree. And so this actually, I put this in because I think it's relevant to the story. Jim Seitz, the student that I had apprenticed under, the graduate student, was married with 2 kids, and his wife could not wait to get out of fertility flats. That was what they called the married graduate student housing back in those days. So Phyllis Liu, who's not here right now, I can say what I want about her. Liu Shijung is her, I guess, formal name. Had gotten her PhD in plant physiology and was already set for a postdoc in biochemistry. And I would say that we had a wonderful existence for the rest of our stay at Cornell. Well, 40 years, I'm married 40 years, something worked. But in particular, we would come in to work at noon, and then at 6 we would have dinner on campus and work until midnight, and then I would take her home, drive her home, and come back in because she put her hair up in curlers. And so that gave me an extra 4 hours, so I would go back at 4 in the morning. So these are actually very good working hours, as you'll see later. So I really didn't know what to do with this dilution refrigerator. I mean, Dave Lee had told me to measure some properties of solid helium-3 through the nuclear spin ordering transition, but no one had a thermometer that would stay in thermal equilibrium with the helium-3 to the temperatures where nuclear spin ordering was expected, 2 milledegrees. Actually, the actual temperature is about 9/10 thousandths of a degree, so I would have been in even worse shape. So there was a student named Lynn Corcini who had read a paper by a guy, unknown theorist, that wrote this article on the effect of Leggett and Rice. And of course, that's Tony Leggett, who, well, I'll keep telling the story. Leggett had suggested that if you measured spin diffusion in liquid helium-3 as a function of magnetic field, you'd get different results. And it would be, of course, it's always strongly temperature dependent, but actually it would turn over, and in fact the spin diffusion coefficient would decrease. And so Lynn Corcini needed to use, if I go back here, the data down to the dilution refrigerator temperature. You couldn't tell which color dots went with one of these 3 theory curves. And so we decided, Corcini went up to me and asked if we could use my Pomeranchuk cell. So this is my Pomeranchuk cell, and then he added a heat exchanger. We did the spin diffusion down there. And then, in fact, it's amazing what difference it makes going from down to 15 milledegrees versus going down to 6 or 7 milledegrees. And it was very easy to tell. And moreover, Tony Leggett was right. And so I said, this guy's pretty smart. And so later on, you'll see that plays a part in this story. Well, so going into the last year of this was done, in my 4th year of graduate study. And so that summer, I went to Dave Lee because my wife was then going into her 2nd year of a 2-year postdoc, and that gave me 1 year to actually get my PhD. So I asked Dave Lee what I should do, and he said, well, simple, just measure some property of solid helium-3 through its nuclear spin ordering transition. No one had seen that transition. In fact, people thought it was 2 milledegrees. It was actually quite a bit lower. And so I really didn't know what to do. And then the Wheatley group that had looked for superfluid helium-3 all the way down to 2 milledegrees had sent a preprint where they had looked at the shift in melting temperature at constant pressure and found that it depended strongly on the applied magnetic field. So these are the Wheatley data in a field of 6.3 kilogauss. We used kilogauss back in those days. And theory suggested in twice that field that you would have this very small effect. So I looked at that and said, wow, this looks very exciting. Now I look at this, I says, this can't possibly be right. But it's a good thing I didn't know very much. So I tried this experiment, and in fact, sure enough, I got basically, with scatter of about 1%, I got what the simple theory curve talked about. Predicted, but in fact, I kept trying to get better sensitivity with my thermometer, and ultimately 2 other graduate students who had been impatiently waiting to get this large iron core electromagnet that we used. We didn't have superconducting magnets back in those days, and so they went to Bob Richardson and Dave Lee and argued that I should have to give up this magnet, which of course I needed for my experiment. And so for that, they shared the Nobel Prize. Because if I hadn't given up the magnet, I would have never done the experiment that actually resulted in the discovery of superfluidity in helium-3. And so I decided I would keep my apparatus cold, because when those guys cool down, I mean, what's true is that everything contracts when it's cooled, almost everything anyway, but things contract at different rates. And so you run the risk that when you cool down that a leak will open up, in which case your vacuum space has helium gas in it, and it's poisoned. You can't do an experiment. So I decided I would wait until they found out whether their experiment is working, or whether a leak had come in, or electrical lead had fallen off, or something like that. So I sort of thought about some simple experiment I could do without a thermometer. And so we measured, actually John Wheatley's group and I had measured the helium-3 melting curve down to about 3 millidegrees, and I expected that below that I could just extrapolate that curve somehow. And so I decided I would compress at a constant rate, converting liquid to solid at a constant rate. So this is the pressure. This is now you guys I have to explain to students what a strip chart recorder is. All the data came out on strip chart recorders, so the paper moved underneath the pen, which moved up and down and recorded the signal. And so this is it's cooling, pressure's increasing upward, and time is increasing to the right. Here I rebalance the bridge that measures the capacitance, that measures the pressure, and it keeps cooling. And then at this point that I later labeled as A, I saw a very sharp decrease in the rate of cooling. And I had interpreted this that the metal bellows had struck some solid helium-3, because we didn't know where it grew inside the cell. And so I think I probably said something like, darn, or something worse than that anyway. Actually, Lynn Corcini, this other student, would add these words in my lab book. I mean, when I'd said something that looked bad, he would then put in a few expletives, which were never deleted. Anyway, so this was actually the day before Thanksgiving, 1971, which is, of course, in November. And so I decided I would use this 4-day holiday to pre-cool the helium-3 as cold as I could get. So the base temperature of the dilution refrigerator was 15 milledegrees. This time I'd started at 22. So here we are the next Monday, and I'm doing the same experiment. I'm going a little bit faster. Cool, cool, cool. I guess I should do it in a higher voice. Cool, 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 cool. Rebalance bridge. Cool, cool. And then there it is again. And this strange feature, which I interpreted as something going wrong, I went back and looked at the pressure where that had occurred, and it turned out the pressure had reproduced itself to a part in 100,000. And I said, there's no way that this can be some chance heating event with a very different starting conditions. This had to be the signature of some highly reproducible but totally unexpected phase transition inside this mixture of liquid and solid helium-3. And as I tell you this, I've done this so many times, but the hair still stands up on the back of my neck, because I still remember the excitement, how I felt when I realized what was going on there. So anyway, I wrote in my lab book, it doesn't look very exciting, the rate of change of helium-3 pressure with time changed abruptly at this capacitance bridge setting. This had occurred on that last compression, too, at a point which was within roughly 2 parts in 100,000 of what I'd seen. That belies the excitement that I felt, I can assure you. But so eventually we found these transitions both on cooling. So this is melting pressure versus time. This was originally called the glitch, but when it came time to publish, you had to give these things, scientific names. So we called this one A, and this one B. Now it's quite ironic that this phase is the state. This is the transition to a superfluid state, which had first been studied by Anderson and Morel, A for Anderson. And this was a state which had first been predicted by Balian and Wertheimer. So I couldn't have been more right. But anyway, so here they are also on warming. And there was something else, though, that was kind of remarkable, and that is the change in pressure between any two temperatures on the melting curve is essentially just 1 over the difference in molar volume times this liquid entropy dt. Solid entropy, solid entropy, liquid entropy is negligible. And there simply wasn't enough entropy to explain the large change in melting pressure we saw. This is, presumably this is about 9/10,000ths of a degree. So something very strange was going on, And this is a conversation I had with Bob Richardson. He was writing in my lab book, and this is something about a kink in the entropy curve and stuff like that. It's all wrong, okay? But this is probably the beginning of the period where we felt that this transition had to be in solid helium-3. After all, Wheatley had looked for superfluid helium-3 all the way down to 2 milledegrees, but his experiments were all done at saturated vapor pressure, because you can get colder at saturated vapor pressure than at melting pressure. If he'd done the same experiment at melting pressure, he probably would be here giving this talk today, although he died. Maybe he wouldn't be, but maybe he would have lived longer. So anyway, so here we have the existence, we published this result. When you have something, you don't know what it is, and it seemed very trivial for you to actually make this discovery. You figure that someone else is going to do the same experiment. So published evidence for a new phase of solid helium-3. This thing sailed through the reviewing process without modification. It was published. Of course, the data is all correct, but the interpretation was 100% wrong. Okay, so anyway, this is the cell that I showed you. But then I began to worry that maybe, in fact, this transition wasn't really in the solid. I mean, we didn't really know. And so I decided I'd put a large NMR coil. I warmed the apparatus up, put a large NMR coil that would sample both the liquid and solid helium-3. We didn't know where the solid was forming. In fact, I'll tell you about that later. But so then what happens is the liquid has a rather small magnetic susceptibility. It's a Pauli susceptibility independent of temperature. But the solid has this huge, nearly ferromagnetic susceptibility. So most of what I was looking at here is solid. And there was a little change at the A transition, a little change at the B transition. And we said, well, okay, must be some subtle effect in the solid. And then nature intervened in the form of a squirrel. This was actually outside my window in California, but a squirrel just like this had been running along one of the high voltage power lines that brought electricity to Cornell University. And when he tried to jump off of it, his body managed to short out the insulator. And his carbonized body was a good conductor, and it brought down the entire power grid at Cornell for just an hour. But when the power came back on, I found that one of my pumps that was pumping on a pot of liquid helium inside this exchange gas can, vacuum can, had leaked air backwards. So I had a block of solid air in this pumping line I had to warm up. When I cooled back down, a leak had opened up in my inner vacuum can. This was, I couldn't do anything without that. And so, I mean, it was really terrible. Right in the middle of this discovery, I had this terrible event. So I patched it up, but in fact, the standard technique in those days was you'd pump on the space where the helium was leaking into, the vacuum can, and then you would dump a mixture of glycerin and soap. This is glycerin, and the soap was ivory flakes. It's baby soap, basically. And you pour that and hope it got sucked in, but it didn't work for me. And so then there was this first-year graduate student who I felt my job was to keep him away from my cryostat. Okay, he was apprenticing under me, but I wouldn't give him any big jobs. And so he said, "Gee, Doug, can I fix the leak?" And I was already in the machine shop machining new parts. And I said, "Sure, kid, go to it." And he made a pot of, must have been about 1.5 liters of this glycerin and soap, and dumped it on this vacuum flange where all the pumping lines went through, and kept dumping it and dumping it. And what he did was warmed up that flange enough so that the glycerin and soap actually penetrated into the leak, and that got rid of it. So one of the things I feel worst about is that neither Bob Richardson, Dave Lee, nor I thought to invite Willie Gully to Stockholm. So if I ever go back, I hope I can invite Willie Gully. But anyway, so this is what I just described there. And so what that did was gave me a chance to think about how I could differentiate the liquid from the solid NMR signal. So I went to Michael Fisher, Daniel Fisher's father, for those that don't know, and I asked him how he thought solid helium-3 would grow inside a Pomeranchuk cell. And I can't remember if I had to explain to him what a Pomeranchuk cell was, but he said, you physicists never worry about surface energies. They're important. He says, probably the solid will only nucleate on the surfaces of, inner surfaces of your cell, and if you're lucky, only in 2 or 3 spots. And it turned out that was exactly right. But that got me thinking, and I said, well, okay, if I do an NMR experiment where the magnetic field is actually higher at the top than at the bottom, the other way around, then if I apply a single RF frequency to the NMR coil, I will get resonance in a very thin layer. If I move that frequency upward, that resonant layer will move downward, and vice versa. This is actually an early form of MRI. It's two-dimensional MRI. But Paul Lauterbur, who shared the Nobel Prize for MRI, actually told me he read my paper the day it came out. So you never know. Anyway, so these are MRI photographs, two-dimensional, and this is all liquid. The pressure transducer was slightly magnetic, and so it gives you a little bump here. But as I start cooling down, going solid, you can see these solid peaks really get larger and larger, and I actually have to change the gain of the strip chart recorders. Eventually, in fact, the liquid signal was only a couple percent of as high as the solid NMR signals. So the question is, this is actually below 3 millidegrees already. What happens when I get to the B transition? So this is real data now, except that time is now going to the left and pressure is increasing downward. So that's because you like to think of these things as peaks, but they're actually troughs. They're absorption peaks. So anyway, so this is low frequency to high frequency to low frequency, and over again. This structure is the mirror image of this one, except that all of these peaks have gone up by a little bit because I'm growing more solid. And so then I started looking at this liquid signal, and it had been flat across the bottom above 3 millidegrees, above the A transition, and suddenly it looked badly distorted. And then I looked at the next one. Here I'd gone through the B transition. And the liquid NMR signal had dropped by a factor of 2. Wow. The only way I could figure out what had happened was the formation of Cooper pairs, one with a spin up and one with a spin down. Now, that wasn't exactly right, but that was close. So I wrote in my lab book, this is 2:40 in the morning. Now, I tell you, that is a really good time. No one will bother you at 2:40 in the morning. And there's less vibrations, less electrical noise. It is the time to be in the laboratory. So keep that in mind. Have discovered the BCS transition in liquid helium-3 tonight. And this was so exciting. Then I ran around the basement of Clark Hall looking for some other graduate students to share this exciting news with. Turns out I was the only person in the basement of Clark Hall. In desperation, I went up to the 6th floor, hoping that a theorist had fallen asleep at his desk. But it wasn't true. I was the only one in the entire physics building that night. And so at 4 in the morning, I couldn't stand it anymore. I called up Dave Lee, my thesis advisor. Now, I encourage you to do that, but you'd better be right. Dave Lee called me back at 6 a.m. for more details. I got no sleep that night at all. It's kind of interesting because the phone call from Stockholm came at 2:30 in the morning. And that phone call, I have it on my machine. The phone rings. It's on my wife's side of the bed. She never answers it. I jump out of bed in my pajamas, run around, pick up the phone. I say, hello? And this guy says, hello? Is this Douglas Osheroff? I said, yes, it's 2:30 in the morning. He says, I know that, but I have a matter of some importance. If I would, my name is Carl Olof Jakobsen, Secretary General of the Royal Swedish Academy of Sciences. And, of course, once he says that, I know exactly what this phone call's about. I got no more sleep that night either. Anyway, so this is a picture of me standing, self-portrait, I should say, standing next to this large iron core electromagnet whose absence played such an important role in this discovery. Now, the first time I gave a talk such as this was actually to the American Physical Society. No, pardon me, bite my tongue, to the National Science Foundation. And afterward, my program monitor comes up to me and says, Osheroff, do you mean that you'll do better physics if I give you less money for equipment? So if that happens, you can blame me. but only if it's in the United States. So then I decided, clearly the B transition was in the solid, but we didn't know about the A transition in the liquid. B transition was liquid. And Dave Lee said, we better go back and look at that A transition, see if we can see evidence for antiferromagnetic resonance shift. And so this little red thing was the all liquid signal, and this huge ugly looking thing was mostly solid. And so as we cooled below the temperature of the A transition, what we found was that the solid didn't move at all, but the liquid NMR signal moved out from underneath the solid, and as we continued cooling, it moved to higher and higher and higher frequencies. And ultimately, when we saw the drop in pressure at the B transition, the liquid signal disappeared as it ran back underneath the solid. This was actually, Dave Lee was there for this. This is the only time he was there when something critical occurred. And so, well, we wrote up another Fizerev letter. Now, we were kind of embarrassed, of course, we'd gotten it wrong the first time, so I entitled this New Magnetic Phenomena in Liquid Helium-3 below 3 milledegrees. Well, I don't know who got this thing to referee, but he rejected it. He said, these guys don't understand how to do nuclear magnetic resonance. The NMR frequency is not temperature dependent. And so we actually, this was rejected twice. Ultimately, I think Jim Krumhansel got he was an associate editor for Physical Review Letters, and he got it published, but it took a long time. But by that time, we'd actually sent the preprint of that paper with this figure in it, which showed this is now, let's see, what am I looking at here? The longitudinal resonant frequency squared minus the liquid frequency squared minus the solid frequency squared. If you plotted it this way, it was all the magnetic field dependence. This is a factor 20 difference in magnetic field. Collapsed. All the data collapsed to a single line. And so we didn't understand that, but when things collapse like this, we figured it's got to be easy for theorists, so we sent a preprint of this to Tony Leggett. Of course, it didn't get published for quite a long time, and it didn't take Tony very long at all to understand what was going on. So Tony thought about Cooper pairs. Now, I don't know if he thought about them this way. They don't really do this. They don't orbit about one another, but they have angular momentum. And so he realized that if the minimum energy configuration for the two spins would be for them to be parallel to one another. And then the projection along which the spin was zero, which he calls D here, would be parallel to the orbital angular momentum. And so this is where he started. But then he thought about what would happen to the frequency. Well, it turns out that as you pull the D vector, this is D vector, away from the orbital angular momentum vector L, it processes in a shallow figure 8. But it wants to be parallel, so that's an added torque. And that added torque would cause the spins to process faster. But then Tony did, this is the difference between a really bright theorist and someone who's brilliant. Tony then thought, what happens if I apply an oscillating magnetic field rather than being perpendicular? So it's rotating, basically, in the plane normal to the applied magnetic field. What if I apply an oscillating field parallel to the magnetic field? Then he realized, in fact, that would drive the D vector in the XY plane here. And, in fact, it would have a resonant frequency which was independent of magnetic field. And then, of course, what he found was, in fact, that this frequency was related to the shift in NMR frequency we saw here. So when I went, after I left Bell Laboratories, after I left Cornell for Bell Laboratories, I think the first experiment I did was to test this idea of Tony Leggett's. Now, people said, well, an NMR resonance, which is independent of magnetic field, it's going to be very sharp. And so you look for a sharp NMR line very differently than you look for a very broad one. No one found this resonance. And then I said, okay, the theorists have to be wrong, even Tony Leggett. I said, if it's a very broad line, how would I look for it? Well, I mean, you can't sweep the frequency because you need a tank circuit. This is a low frequency, so you really have to do something else. I said, okay, I will sweep the temperature. And so when you sweep the temperature, you get this very broad resonance out. But if you figure out what the peak of that is and compare it, the longitudinal resonant frequency with the transverse NMR, that's conventional NMR frequency squared minus the Larmor frequency squared to the 1/2 power, these data collapse on the same line. So it was pretty clear that Tony's ideas worked. But then we went beyond this because Tony had suggested, in fact, that you would see a longitudinal resonance in both the A phase and the B phase, and they would be related to one another. And so I basically, this line is taking the A phase data and comparing it with B phase longitudinal resonance data. And there's a factor of square root of 5/2 that makes up for the fact that they're different phases. Anyway, the bottom line is this, I think, was really the proof that these two states were superfluid phases, and in fact, we knew exactly which phases they were. So this is my Pomeranchuk cell again, and the talk is almost over. But I put the names of people who made important contributions to this discovery, starting with Pomeranchuk and Anuferev for their Pomeranchuk cell, Bardeen, Cooper, and Schrieffer. Without BCS theory, Phil Anderson and others wouldn't have predicted superfluidity in helium-3. Bloch and Purcell, without NMR, I wouldn't have done any of these experiments. Edwards and Hall for their dilution refrigerator. Hamill, Wheatley, Landau, and several others for understanding the normal state of helium-3. Strady and Adams for the strain gauge, which is a remarkable device. It has resolution of maybe 10 parts per billion, and it dissipates no more than a 10 billionth of a watt into this apparatus. So the point is that without any one of these names, I suspect that I wouldn't have made this discovery, and probably no one else would have either. So the point is we didn't really do this alone. And I would say in general that advances in science are seldom made by individuals alone. They really result from the progress of the scientific community asking questions, developing new technologies to answer those questions, and sharing their results and their ideas with others. This is how advances in science are made, and not this way. This is Tony Leggett sharing the Nobel, he actually was shared the Nobel Prize, of course, with Abrikosov and Ginsburg, all for their work on BCS states, but some of them were neutral and some of them weren't. And I think, here, whoop. And this is Dave Lee, Bob Richardson, and myself. If you look very carefully, you see that Dave Lee and Bob Richardson have oriented their medals so that Nobel's head is upright and mine is tilted sideways. Don't tell them that. They'll take the prize away from me. Anyway, thank you very much for your attention. I don't know if people want to ask questions. I'll be happy to try to answer them if anyone wants to.
We thank Doug very much for the fascinating talk. Let me just say that in addition to everything else, we learned a little bit about how experiment and theory can go hand in hand. And we'd really appreciate a few questions.
Yeah, I should add to what Joe just said. The most enjoyable experiments that I've ever done have been done hand in hand with theorists. I mean, it's just a wonderful way of working. I wish I could do both, but I do one of them fairly well and one of them not at all. No questions? Yeah, yes. It's the same one. Yeah, which is amazing. They always said the Landau school was very broad. And I think this is an example of that.
May I ask you, in retrospect, would you be able to detect this without NMR?
Well, we would have certainly seen the kinks. Now, we would have had to come up with another way of differentiating knowing whether these transitions were in the liquid or the solid. And I mean, of course, once you realize that there's a jump in the heat capacity at the liquid superfluid transition, then you understand it. But we weren't thinking like that at the beginning. We were really thinking about the solid. So that's a good question. I don't know. Certainly, though, I think to really understand these things, you really needed NMR. I mean, the NMR was a real key to the nature, probing the microscopic nature of these states.
Any further questions, comments, suggestions?
Let me just say that I give this talk generally to much younger audiences than this, but they ask a lot more questions.
Let's thank Doug again, and also thank the organizers for this wonderful meeting.